Okay, so moving on from there, let's talk about descriptive stats. So when it comes to your sample, um, there's a lot of different things your sample as well as your results, like your dependent variable. Um, there's a lot of different data that you kind of need to describe, and we have a lot of standard measures that um, are usually required um, when you write a paper. Now, these include things like what's typical of the sample, how much do people in your sample vary, say their scores on your dependent variable, how strongly are variables associated, and also graphing this information. Okay, so um, when it comes to something known as central tendency, we're kind of describing what's typical of the sample. Okay, so what's the most common value? What's the average value, as well as the median? So when it comes to measuring central tendency, those are the three measures: mean, median, and mode. Okay, so and by the way, we'll talk a bit about how these are either equal or not equal depending on what your sample looks like. So the biggest one that you're going to report in pretty much all papers is going to be the mean. And this is simply the average. So you're going to take all the scores and divide them up. Take all the scores, add them up, and then divide it by the number of participants. Just the average. Okay. Um, you might also, usually we'll also do the mean separately for each condition. So, if I run an experiment looking at number of mistakes made with a cell phone driving versus number of mistakes made without a cell phone, I want to report the mean um, for both of those conditions. So how many mistakes on average were made with the cell phone condition and in the non-cell phone condition separately. Okay. Um, Next one is going to be median, and this is just, if you remember what percentile means, the 50th percentile score. So percentile, if you don't remember, just means um, how many how many numbers did you score ahead of? So, for example, on an exam, um, if I got 96 percentile, that means I got better than 96% of the class. Okay. If I got 10th percentile, that means I got better than only 10% of the class. And obviously, 50% means I got better than 50% of the class. So it's just the numerically middle number. So if I lined up a whole bunch of numbers, um, say like 1 to 5, the median. So 1, 2, 3, 4, 5. The median would be 3. Just taking them, ordering them from smallest to largest. Take the number in the middle. Um, if you have an even number of numbers, so you have like say 1, 2, 3, 4, 5, 6, you're just going to take the two middle numbers and average them. So that would be the median of 1, 2, 3, 4, 5, 6. The median would be 3.5. Okay. And then the mode, lastly, is the most common score. So if 10 people got, say, 60%, 20 people got 55%, and so on and so on, then and 55% was the most common score, that would be the mode. Okay. All right. So when it comes to our data, whether you're graphing kind of variables, even something like age, whatever it might be. I mean, there's a million things you might do with frequency distributions, but it can tell you kind of what the spread of scores looks like. So typically you'll do what's called a histogram. And this is just grouping people by the number of times they, or the number of people rather, that got each score. It's a histogram. So let me show you an example. This is a histogram of something. So what the y-axis is, this is the number of observations or number of times that they got that score. These are the actual scores. So say they do some memory test and they get anywhere between 1 and 20. Well, I can see from the histogram, okay, what are the distributions of the scores? So I can see 15 people got 8 right, 10 people got 15 people got 8 right, 10 people got 15 right, 8 people got 16 right, so on and so on. And this kind of tells us, this can tell us different things about our data that are often important. So when it comes to a histogram of the data, or and by extension a distribution of the data rather, a question we often ask is your distribution normal or is it skewed? Okay. So just imagine, and we'll look at examples of this. A distribution can take on many different shapes, right? So you can have, a whole bunch of scores kind of here, and then less as you go higher. You can have a whole bunch at the higher point, and then less as you go here. You can have it normal, where, as we'll look at in a minute, the scores are bunched kind of around the average or the mean. And then, or you can have what's called a bimodal distribution, where you have, say, two peaks. So like a lot of people here and a lot of people here, and then not a lot here, not a lot here, not a lot here. You don't have to remember those all right away because we'll go through them individually. But just remember that a distribution can be shaped various ways. So when it comes to a distribution, two often ways it can take shape are normal versus skewed. So this is a normal distribution. Okay. Just checking that I'm recording. So normal distribution, it's shaped like a bell. And then in fact, they often call a normal distribution a bell curve, because that's what it's shaped like. So when it comes to a normal distribution, that's often a requirement for a lot of statistical tests that we do. So when you run whatever statistical test, p-test, I think a correlation, most tests require some degree of normal distribution. And it kind of messes up the calculations if it's not a normal distribution. But in terms of a normal distribution, one key thing is that, like I said before, the frequencies are kind of clustered around the average. So let's say the average score is whatever this is here, whatever number this is. That's going to be, that average is going to also be the most common value. Okay. So let's look at a real world example. Let's say I'm looking at height of the population. Well, obviously I draw a sample from that population, and I might expect that, let's say the average height is 5'10". Okay. Well, 5'10" might be the mean, but it's also going to be the most common value. So so it's most likely, out of all the people on the planet, the most frequent height is 5'10", but it's also the average, and those are not the same, as we're going to see. but they are the same in a normal distribution. Okay, so that's kind of one of the defining characteristics of a normal distribution is that the mean, median, and mode are all going to be the same. So again, if you lined up, say we're dealing with heights here, and 510 is both the most commonly occurring value, the most common height, it's also the average, then that's one criteria for a normal distribution, in addition to median. So median, again, is if you line all the numbers up, smallest to largest, what's the middle number? So if we took all the heights of the population and we ordered them smallest to largest, what would be the middle number? Probably be 510. So in that case, again, with a normal distribution, the mean, the median, and the mode are all the same. Okay, that's kind of the defining characteristic. Remember, mode is the most common value. See the mode here, most common value. On the other hand, when your distribution is not normal, when it's skewed or in some way different, you sometimes end up with different values for mean, median, mode. So here's an example of that. Notice how the mode here, so the most commonly occurring value is 1, whereas the mean is actually 3. And the median is 2 point something. I guess presumably there'd be more numbers here, but you get the point. So when the distribution is, so remember that when the distribution is not normal, it's not like this, the mean and the median and the mode all take on different values. And again, there's lots of different distributions. Some of them, they all differently affect these values. But again, the key there is that with a normal distribution with this bell curve, 3 are the same. Okay. So again, normal distributions are when most scores are centered around the mean. Or in other words, the mean and the mode, remember mode is the most common value, are the same. Skewed distribution is when most scores at one end of the scale are clustered. So that's what we have here, right? We have, rather than most scores being clustered around the average, most scores are clustered around one end of the scale. Okay. And this is important to know because a lot of statistical tests require some degree of normal distribution. And some of them actually change depending on your distribution. Just for example, you don't know this, but a t-test or a z-test requires a normal distribution. A t-test requires a non-skewed distribution, but it doesn't have to be exactly normal. An analysis of variance is built on a skewed distribution of probabilities. But again, you don't know that. Okay, so when it comes to describing our scores, describing our averages or spread of our dependent variable, whatever variable we're looking at, there's several things to consider. So first of all, outliers, range, standard deviation, and variance. And we'll go through each of these in just a second. So range is, just as the name suggests, what's the highest score versus the lowest score. It's kind of the simplest measure of spread. Okay. Highest to lowest score. And by the way, as we're going to kind of see, different distributions can affect these different measures. So just to kind of foreshadow, range can affect something like outliers can affect range, but not necessarily some other factors like median. Actually, outliers will affect each of these, but don't worry about that for now. Okay, so next thing to consider is something known as an outlier. This is just what it sounds like. This is a value or several values that are really distant from the rest of the values. Okay. So, for example, if I ran a survey and asked people, how many drinks do you consume per week? So we have kind of a bit skewed of a distribution. Maybe there's, or yeah, it is. I guess it is pretty skewed. So most people kind of cluster around this 4 to 6 mark, and then less and less as we get away from there. But except for these ones, these are what we call outliers because they're really different from, say, the mean. So the mean is like 4 to 6. So is the mode, um, or rather, I'm sorry. Actually, the mean is probably more like over here. I'm not sure what exactly the mean is, but bottom line is that these scores out here are very different from the rest of the scores. The rest of the scores are, at least to some degree, within each other, but except for these three, these are outliers that are drinking 100 or 134 or 50 drinks per week. So we should be concerned with outliers or be aware of them because they can affect our mean. Okay, our mean can really get modified by the presence of only a couple of outliers. So in this example here, the mean was, oh, actually, I was a bit off. Or yeah, I was sort of close. With the outliers, it's 8.91. Without the outliers, it's 7.51. The average number of drinks per week. So the kind of outliers, especially like a really extreme outlier, can affect our estimate of the mean, but it's maybe not telling us the whole story because though it might affect the mean, it's only one score or even a couple scores out of our total sample. So yeah, like I said, just these few over here can really change our mean. Now, how do you think median is affected by outliers? Think about that for a second. Will it be affected to the same degree as mean? No, it actually won't, and that's sometimes why we use median instead of mean. So with a median, you can add an outlier, but because you're taking the middle score, the outlier is not going to affect that median as much as it's going to affect the mean. So let me give you an example. Let's say I was looking at, well, we'll use the same example here. If I were to, no, actually, I'll use a different example. Say I was looking at something with income, and I had, most people around like 40,000 or 30,000 or 50,000 yearly salary. Well, okay, so the mean might be, let's say, 40,000 per year. Now, if I throw in an outlier there, like say just one billionaire, um, it's going to really distort that mean, right? Because even though it's say like a small number in my sample, that one or few billionaires is going to really give a different impression that's actually than is actually accurate. The mean is going to really, just those couple outliers, couple billionaires are going to really distort what the average is. It might give you kind of a false impression of, you know, what the actual income is. Meanwhile, that income is being very skewed by just this one or few individuals. So that's why when it comes to measuring income, median is actually preferred. Because let's say you have just that one billionaire, well, it might shift the median over one number, but it's not going to do anything beyond that. So let's say if you have a median and then you add like 2 billionaires to that, it's not going to make much of a difference compared to mean, where it is going to make a big difference because you're taking the average. I'll put an example of that in just a few minutes. Okay, so moving on from there, when we're looking at another measure of spread is standard deviation, and this is just going to be a square root of what we call variance. Variance is how far each measure is from the mean. You're going to take that and you're going to take the average of the squared difference scores from the mean. Right? So here's what that looks like. Average of the squared difference of the scores from the sample mean. Take the score, subtract the mean, square it for all the participants. Then divide by the number of participants minus 1. Here's an actual example. So if you had 8, our mean here is going to be 13. That's what X bar means. N is just going to be number of observations, number of participants. So there's our mean, the 13. There's our number of participants. So to get the variance, all you're going to have to do is take this number, subtract the mean, which like we said is 13, and do that for each value. So 14 minus 13, 18 minus 13, 15 minus 13, 17 minus 13, 9 minus 13, 10 minus 13. Okay. That's going to give you these numbers. And then what we're going to do is square those. So see, that'd be 25, 1, 25, 4, 16, 16, and 9. And then lastly, we're going to divide by our sample size minus 1. So that's going to be 7 minus 1. So remember, we had seven numbers here. Okay, pretty straightforward. This is going to, again, give us an estimate of how much the numbers vary from the mean. Just a couple things to think about. So why does it matter? Does it matter if things are negative or positive? Well, not really, right? And that's why when we square them, we lose the negative sign, because you're not really considered here with which direction do they vary. Are they below or above the mean? You do that with other calculations, but you're just interested in how much do they differ from the mean. So that's why you square the negative values. You also square them because if you added these numbers up, you would get 0. So you have to square them first to get your variance. Then again, divide by sample size minus 1, you get 16. That's our variance. Okay. So we kind of think of variance as, how far each value is from the mean. Well, you can kind of imagine what that would look like in terms of our histograms. So something like this is going to have a lot of variance because the mean here, well, yeah, I guess numbers are pretty spread from what that mean is, right? They're not all kind of clustered around the 13, 14, 10, 11 range. Okay. Oh, just one more example I wanted to give. So I was talking about median earlier. Now, median is not affected by outliers. Well, let's look at this example here. So whatever the median of these numbers are, that would be, I think, the 15. Yeah, the 15. So if that was our median and we added let's say 1,000 here. So one other participant had a score of 1,000. That would obviously affect our average, our mean, quite a bit, right? Our average would go up substantially, even though it's just one outlier. We added 1,000. However, that wouldn't really affect the median so much. So the median might go from 15 to 17, I think. Or no, maybe it's whatever the number is. Bottom line is it might shift over one number, but it's not going to be drastically affected by that outlier, whereas mean would be. I'll give you another example of it. Okay, so outliers can obviously skew our mean, and they can obviously also affect our variances. So if the next highest score is 10 and we add a 21 in there, well, that obviously changes our range. So 2 to 21 instead of 2 to 10. But what happens if I delete 21? Well, I get different results. This is kind of where outliers can really mess up your data. Just having that one participant or a couple participants that are way far away from the mean. So, for example, here, again, this is with including that 21 score. This is not including the 21 score. So the 21 is the outlier. It, of course, affects our mean, not surprisingly, but it also affects our variance and also our standard deviation. So again, that's where this one number that's really off can throw off your mean and your standard deviation. While we're on the subject of standard deviation, it's kind of just an extension of variance. It's more useful though, and it's just going to be a square root of that variance. Okay, so you take that number you got here, and then you're going to take the square root of it. So 4. That's going to be standard deviation. Okay. And you typically report both the mean and in conjunction with it, report the standard deviation as kind of two common descriptive stats. Okay. So on to standard deviations, those of course are important and they can affect our distribution, which we'll talk about in just a second.